Good afternoon to everyone. I welcome all of you to the 92nd lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Professor Tapan Kumar Kar. Professor Kar received his PhD from Jodhpur University in the year 2004. He carried out his postdoctoral work at the Yokohama National University, Japan, for a couple of years during 2005 to 7. He started his teaching career as a lecturer, and by 2005 he became the assistant professor in Bengal Engineering and Science University, Howrah. He is currently the professor at the Indian Institute of Engineering, Science and Technology, Shibpur, since 2011. In the year 2021, he has been elevated as professor, higher administrative grade. He has a vast teaching experience of 27 years and a research experience of 29 years. He received the certificate of highly cited research in biosystems in December 2016 from Elsevier. He has been included in the list of top 2% scientists in the world in all disciplines from India, based on the Stanford University study in the year 2020 onwards. He is the Joint Secretary of Biomathematical Society of India as well. Professor Kar's research areas include dynamical systems, stability and bifurcation theory, population dynamics, and mathematical ecology. He has several notable publications in his area of expertise. He has delivered several lectures and talks in many conferences across the world. During his career, he has guided 25 doctoral candidates. He has authored almost 2,000 international peer-reviewed articles and has an H index of 38. He is also one of the editorial board members in Mathematics and Computers in Simulation. So with this short introduction, now I invite Professor Kar to deliver his lecture. Over to you, Professor.
Okay, thank you, Professor Senthil Velan, for inviting me for this nonlinear studies, nonlinear dynamics and complex analysis systems lecture series, and also also introducing me to your students. Good afternoon to everybody, every students, both from PhD and master students. Today, my lecture is Asymptotic and Short-Term Responses of Perturbation, a mathematical comparison of stability measures. I have kept considering that most of the students are coming from the master's level, and for PhD level, very basic items are I have decided to explain here. I am not going any core topics that I am now publishing with my scholars and other students. So I think you will understand, and more further, if you need further knowledge about this subject, I will give you some references also. You may study those references. So now I am going to my presentation mode, and during this presentation, my video cam will be off. So if you have any question, you may ask at the end of the talk, and if there is any network issue or any other, so you please send a message or call me that I am disconnected. Hello, students. Is it properly visible?
Yes, sir. Yes, it's visible.
Oh,
yes.
Okay. So, Professor Senthil Velan already introduced me about my research domain. Most of the publications comes from the mathematical ecological modeling and epidemiological modeling. And here, if I give any example, maybe arise from the mathematical ecological problem or epidemiological problem, though, but I have kept the lecture so that if any students comes from other field or physics or anywhere, so that they also get some idea about the topics. So it is not properly any core example of mathematical ecology or like that. I have mostly given some basic items, basic topics on this asymptotic and short-term responses of perturbation. I hope you will get some idea. So first I will give a brief introduction of the topics. Usually we consider the asymptotic dynamics theory on population dynamics or whatever, epidemiological modeling or nonlinear dynamical system. We mostly consider the asymptotic theory, and that asymptotic theory mainly concerned with the long-term behavior of perturbation. That is, if there is a disturbance, after a long time, what will happen? That dynamics is studied, and that is the asymptotic theory. But short-term dynamics also equally important when we consider any nonlinear dynamical system, and that dynamics perturbed or disturbed by any external forces. Conventionally, most of the researchers focus mainly on the asymptotic stability property near the equilibrium, and something I have checked that there are many lectures are already happened, and already I hope that you got some idea about the equilibrium points, stability, etc. Still, I would briefly describe some portions, otherwise it may be difficult for me to introduce my topics. That is, I will mainly consider the resilience for the asymptotic part, and for the short-term terms. Okay, I am coming later, step by step. Most of the researchers focus mainly on the asymptotic stability properties near the equilibrium. However, the transient dynamics, that is the short-term dynamics, also equally important for the dynamical analysis of any nonlinear system. And usually people think that the short-term and long-term dynamical behavior are almost same, but it is not so. There may be a significant differences of short-term and long-term dynamical behavior of any nonlinear system. And for our that I have mentioned that most of the examples will come from the ecological modeling. So if we consider any ecosystem management, mainly the researchers and also we consider the asymptotic behavior of the system. That is, what will happen after a long time. Transient dynamics can be more significant than asymptotic states of the system in terms of the observation, modeling, prediction, and control of the system. That is, okay. And also, in case of the studies of epidemics, essentially needs focus on transient dynamics, because we do not wait the what will happen after a long time. If any epidemics occur, then we need to consider the immediate behavior of the epidemics, not after a long time. So transient dynamics is very important for this purpose also. And for ecosystem managers and conservation biologists also deal with the short-term responses for due to economic and political reasons. What happened after a long time, it is also important, but it is also important what will happen just starting the epidemic started, or for the political purposes also we need to consider the immediate results, what will happen for the economic purpose also. So short-term responses are also equally important for ecosystem management, for disease control, etc. And long-term dynamics, mainly we consider two things. One is the stability and another is the resilience. And these two characterizes the asymptotic dynamics. I'm step by step, I'm coming briefly on stability, resilience, and then I will move to the short-term dynamics. And this definition is, I think, almost it is maybe known to you. Suppose if we consider a fixed point x naught for the system x dot equal to fx, x belongs to r square. Here I have considered only two-dimensional. Not necessary that we have to consider it is a two-dimensional. Just as a example, I have considered it is a two-dimensional case. And here it is given that for a given epsilon greater than 0, if there is a delta greater than 0, such that for all t greater than equal to t naught is the initial time, norm of xt minus x naught t less than epsilon, whenever norm of xt naught minus x naught t naught less than delta. And if this is happened, then we say that the equilibrium point or the fixed point is a stable, not asymptotically stable. But we are mainly concerned with the asymptotic stable system. Asymptotically stable system is what I am coming later. And what is the meaning of these two, norm of this and norm of this? That is, if we consider a fixed point is here, and this is the neighboring point, and there is another neighbor, that any point, if you start from any point, any initial point here, the trajectory always lie within this domain, that is within this domain. Then in this case, we say that the equilibrium point is stable. But we will measure the stability using eigenvalue analysis. I will briefly describe later. But as I told you, that mainly we study about the asymptotical stability. If we start a point, fixed point, and take a point very near to that fixed point, the trajectory starting from that point will lie in a neighborhood of the fixed point. That is stability. But asymptotical stability is what? Difference between the stability and asymptotical stability is that in the case of asymptotically stable, that trajectory converges to the fixed point. Now look at this. And from now, I will consider only the asymptotically stable point. A fixed point x naught of the system 1 is called asymptotically stable if it is stable and there is a eta greater than 0 such that, look at this, not lies in an interval if this norm tends to 0 as t tends to infinity. It means that the trajectory will converge to the fixed point after a long time. And this is the asymptotically stable case. And we will measure this asymptotically stable state using eigenvalue analysis of the Jacobian matrix that will be discussed now. Now, come to the second characteristic of second characteristic of long-term behavior, that is asymptotic behavior of the dynamical system. Here, what is the resilience? Resilience is that how fast the state of a locally asymptotically stable system returns to its positive equilibrium. That is, suppose here it is the fixed point, a disturbance, this fixed point moves to this point, a perturbation is here. So again, it will come back to this fixed point. If it is stable point, it will come back to this point, this point, this point, this point, come back to this point. But our intention is here how quickly this this perturbation will decay and this perturbation will converge to the equilibrium. How fast? This is the resilience. In case of stability, whether it will come back to it or not. In case of resilience, how fast it will come back to its original position. How fast? That is very important. It is measured as the potential to absorb the disturbances applied to the system and get back to the natural system. And why we are interested on how fast? Because followed by a disturbance, a less resilient system takes longer time. If a system is less resilient, it means it takes longer time to return back to its original position and may suffer a new disturbance again before it reaches to its original state. Aggregation of such disturbance could create a temporary state of the system, and that is very dangerous for the ecosystem. So resilience measure is also an ecological services to be measured in addition to its stability. Stability is okay, but resilience also need to be measured for ecological systems. That is how fast it will come back to its original state. Whether it will come back to its original state or not, that is asymptotic stability, and resilience, how fast it will come back to its original state. And I also using the eigenvalue analysis, how the asymptotic stability and resilience could be measured using eigenvalue. And short-term dynamics is what? As in case of asymptotic dynamics, we have discussed about the stability and resilience. In case of short-term dynamics, we will study three characteristics. One is the reactivity, second one is the maximum amplification, and the third one is the time at which the maximum amplification occurs. What is reactivity? It is the maximum, reactivity is the maximum taken over all initial conditions of the instantaneous rate of amplification of a small perturbations. That is, informally, if I say what is reactivity, that is, suppose this is the fixed point, there is a disturbance perturb to this point. So this is fixed point. This is fixed point, and this is the perturbs due to disturbance. It is perturbed to this point. So immediately after the perturbation, it will decay in this direction, or in this direction, in this direction, or immediately after perturbation, it will move away from this first. Then, suppose for example, it may after this perturbation, it may move in this direction, then it can move to this direction. So there is a, instead of decay, there is a grow, and that grow measurement is the reactivity. That is, immediately after the disturbance, it may not come back to in the direction of the fixed point. It can grow, then it may come back to its original positions. That is very important, and that is the reactivity of the systems. And the maximum amplification, later I will discuss what is the maximum amplification and the time at which this magnification occurs, how you will measure the reactivity, maximum amplification, and the time at which the maximum amplification occurs. Before that, before measuring the how you will measure the resilience, reactivity, amplification, time at which maximum amplification occurs mathematically. First, I will briefly describe. Okay, I am coming this graph later. First, it is a brief description of the linearization. As I know that this is already discussed with you in earlier talk. Still, I have to discuss because I have to consider the Jacobian matrix and corresponding eigenvalues. That's why I am briefly describing here. So, suppose for example, we have taken.
Excuse me.
Hello.
Is there a
Yes?
quantification of? Is there a quantification of resilience towards stability?
Quantification.
Yeah.
Yes, I am coming later. Resilience, how fast, how I will determine resilience and what is the impact, I am coming later. After this eigenvalue, then I am coming later. So this is the fixed point and linearization. Why I will coming this point that suppose we have considered a two-dimensional system dx dt equal to pxy, dy dt equal to qxy, and say fixed point is uv. Fixed point means dx dt equal to 0, dy dt equal to 0. That will give the fixed point uv. And say there is a perturbation. Say this is the fixed point uv, and say this is a perturbation. This is x, this is y, this is x, this is y. So small x equal to u plus capital X and small y equal to p plus, and then substituting here and taking the Taylor series expansion, and we consider that this x and y are very, very small, so neglecting higher part, we get the approximate linearization as dx dt equal to this and dy dt equal to this. And this matrix, this is the del p del x, del q del y, del q del x, del q del y. This is the Jacobian matrix. Jacobian matrix. And this Jacobian matrix is very important. And why we are considering this linearization? Actually, the Hartman-Grobman theorem, somebody of you might have heard the name, that Hartman-Grobman theorem states that, informally I am telling, near an equilibrium point, the nonlinear system has the same qualitative behavior as the corresponding linearized system. So instead of studying the nonlinear system, we are actually linearizing the system near the equilibrium point, and then we are studying the qualitative behavior for the linearized system. And the linear two-dimensional system takes the form, and if you write it in the matrix form, then it is dx vector form, dx dt equal to ax, where A is the vector a1 1 1 2, sorry, matrix a1 1 1 2 2 1 2 2. Now for this system, if you consider a trajectory of the form like this, x equal to this e, not e the same, any other constant, this e is a vector not equal to 0, and lambda is a constant. This is the solution. If we consider this is the solution for this system, then substituting, you will get a characteristic equation, and then from the characteristic equations, you will get the lambda equal to, say, for example, two-dimensional case, lambda 1 and lambda 2. So if you find the value of lambda as lambda 1, lambda 2, whether it is real or complex, then look at this solution. So it takes the form like this: x equal to c1 e to the power lambda 1 t e1 plus c2 e to the power lambda 2 t e2. Here lambda 1, lambda 2 may be complex, may be real, and if look at this xt, this is the perturbation. That is, our intention is that if a system to be stable, this perturbation will be decayed and ultimately tends to 0 as t tends to infinity. So when it will happen? It will happen only when lambda 1 less than 0, lambda 2 less than 0, if both lambda 1, lambda 2 real, and if lambda equal to, say, for plus minus I beta, in that case alpha must be less than 0. In those cases only this xt tends to 0 and equilibrium becomes stable, local stable. Okay, next, here that I have already explained that xt tends to 0 as t tends to infinity. For any initial condition, then only it is asymptotically stable, and that will happen only the sufficient condition is what? That all the eigenvalues of A, that is lambda A, have negative real parts. And if it is real, then negative. Now, the resilience quantifies the stability of an equilibrium. And it is determined how to measure the resilience. That is the using the eigenvalue of the matrix A. That's why I have discussed this linearization and the eigenvalues of the corresponding linearized matrix. Here, the linearized, because we are considering the asymptotic behavior. Asymptotic behavior means t tends to infinity after a long time. So here it is denoted by V infinity, the resilience, and this is measured as minus real value of real value. If it is real, then on real. If it is complex, only the real part of lambda ma. Lambda m is the maximum value, eigenvalue with largest real part. And also in the case of resilience, we measure the return time to the equilibrium. Return time is what? That is the reciprocal of 1 by minus real part of lambda A. So from these expressions, it is clear that a large return time to the equilibrium suggests that low resilience of the phase of the in the phase of the perturbations. So resilience quantifies the stability of an equilibrium. How quickly it will reach to the original state, that determines the resilience, and how long time it will take to come back to its original position, that is return time. And return time, larger return time means resilience is smaller. So this is very important. So as I have already mentioned, that it is measured as the potential, resilience is measured as the potential to absorb the disturbances applied to the system and get back to its natural state. Actually, this resilience approach complements and enlarges the linear stability paradigm and control the strategies for the model phenomena. How it control this approach help to control strategies for the model approach. I will just give 2-3 graphs and I will explain here. And this resilience approach answer to the questions: how far is the system near the tipping point, how to increase basin of attraction, how to prevent critical transition, and how to move a system to another basin. Actually, what happened? Followed by a disturbance, a less resilient system, what is? A less resilient system takes larger time to come back to its steady state and may suffer a new disturbance before it. Aggregation of such disturbance could create a temporary step. That is very dangerous. So resilience approach is also very useful ecological services to be considered in addition to the stability. Here I have considered a system. Just for example, I have a 2-3 research paper on resilience, and here I have just taken this model, not because some students may not understand the model. Just I have considered 2 equations. Here x and y are 2 variables, state variables, and E is considered as a control parameter. And coexisting equilibria can be found from solving these 2, and linearized system becomes this. And here, considering the equilibrium point, etc., we find the characteristic, linearized matrix at this. It is only the control parameter E is there. Now, from here, to measure the resilience, we have to find the eigenvalue with largest real part. In case if trace this, then the real part of the leading real eigenvalue is this, and if this one, then this. And corresponding to this, here two graphs are given. Look at this. Here it is shown an equilibrium point. Return time to the equilibrium point. Here it is, look at this. The control parameter E is taken as the control parameter. Now return time is measured in this way that, look at this, from here to here, there is no change of the return time. Then suddenly the return time jumps. Return time jump, there is a bifurcation. The bifurcation, this is actually in our paper, it is done. Spiral to node bifurcation is happened. So as the return time from this point to this point does not change, so resilience remains unaffected. So here actually in our paper, we have considered E as the harvesting effort. This effort means fishing effort. So how much we can give the effort so that we can take the collect the maximum fish that determine the effort, and this effort, how much we will give the effort so that our resilience remains. That can be determined using the resilience, because if we consider a harvesting effort at which the production is maximum but resilience is very less, that could be dangerous. So we can measure the resilience using the effort. So it is found that from this point to this point there is no change of resilience, and if the production is maximum at this point, for example effort, we can take it, but we cannot take the effort level after this, because during this period the effort level after this, the resilience, that is return time, is suddenly jump, that is resilience will decrease, and if we still use the effort in this part, resilience decreases, resilience is very resilience shrinks, and that what will happen, that it will take very long time to return back to its original positions. So this is one example, and here it is spiral to node bifurcation occurs, and another example is here given, that is this, look at this, from this portion is the return time decreases, it becomes minimum here, and then again return time increases. So there is also a spiral to node bifurcation occurs here, and then so given the resilience profile, an effort exists that maximizes the resilience of the community. So from this graph, it is very much clear that the return time becomes small, minimum at effort level. Say, for example, here it is 1.5. So at this point, the resilience is maximum. So if we need to give our attention more on the conservation than the production, then we can use the effort level equal to 1.5 so that we may get the resilience maximum, that is, it is beneficial for the conservation ecosystem. So it depends on your choice. It needs a balance between the production and conservation of ecosystem. If we give more attention to the production, then we have to find an effort at which the production becomes maximum. If our intention is to ecosystem conservation, biodiversity conservation, then we need to consider the effort level at which resilience becomes maximum. Okay, now the second part, the instantaneous responses, t tends to 0. That three characteristic I have mentioned. One is the reactivity, amplification envelope, and the time at which the amplification maximum amplification occurs. First one is the reactivity. It is the maximum short-term rate of departure from the equilibrium that is given here. This is the larger the reactivity, the faster a perturbation can possibly grow. So after the disturbance, a perturbation occurred, and again, if or immediately if it started to decrease to the direction of the equilibrium point or like this, then no reactivity. But if after the disturbances it grow, then it return back to its, then reactivity occurs. And stable equilibria with positive reactivity are called reactive. And simple techniques to measure the reactivity, again, we consider the linearized system. Any nonlinear system that is near the equilibrium, it is linearized. And it takes the form like this, dx with equal to ax. A is the linearized matrix. And in that case, the reactivity is measured in this way. And just a moment. This V naught can be calculated from the eigenvalue also, but not the eigenvalue of the linearized matrix. It can be measured using the eigenvalue of the Hermitian matrix. Hermitian part of the matrix, that is half A plus AT. You know that this is a symmetric matrix and eigenvalues are always real. So V naught is measured as this. So as I would remind you that eigenvalue of A determines the asymptotic behavior, and eigenvalue of H, that is the Hermitian part of the matrix A, determines its instantaneous behavior. So both the asymptotic and instantaneous behavior can be determined using the eigenvalue analysis, but first one from the linearized matrix and second one from the Hermitian part of the linearized matrix. And here, look at this V naught, the reactivity that is measured from this formula, and that can be measured from here, lambda 1 HA. Lambda 1 is what? The maximum positive eigenvalue of A. Here, the complex eigenvalue does not occur because the matrix is real. So lambda 1, all eigenvalues are real. Lambda 1 is the maximum positive eigenvalue of HA, Hermitian matrix. And this is just an example. I'm coming to the next one. The amplification envelope. Amplification envelope is what? Reactivity is measured as t tends to 0, and this transient response 0 to infinite lies between 0 and infinity. And amplification envelope is what? A bound on the amplification of a, I will show you some graph, then it will be clear. A bound on the amplification of a perturbation that holds for all time. And among the characteristics of the transient dynamics near an equilibrium point, amplification envelope is a very special one, which provides actually the upper bound on the extent of transient amplification as a function of time. And this is measured in this way, maximum of this, that is considering all the initial points, maximum of this norm of this, and that is the matrix norm induced by the Euclidean vector norm. And the amplification, maximum amplification is what? This is the amplification envelope. This is measured in this way, and this maximum amplification is that t greater than equal to 0, for which this rho t becomes maximum. And the T for which this rho max occurs, that is the minimum of T belongs to 0 infinity, at which rho T becomes rho max, that is the T max. That is also very important. When the maximum in amplification occurs. First, you have to draw the amplification envelope, then determine the maximum amplification, and then the time at which the maximum amplification occurs. So, stability, that asymptotic behavior measured by the eigenvalue of the linearized matrix, and the transient instantaneous responses can be measured by the Hermitian matrix. Now, two examples are given here. Suppose dx equal to a1x and dx equal to a2x. Two examples are taken. Both are a1, a2 linearized matrix of any nonlinear system. And here the eigenvalues of both a1 a2 are lambda. It is not necessary that you have to take the two matrices of that. This is just example. Eigenvalues are -1, -2. So in this case, the equilibrium point corresponding to this system is stable node, since all the eigenvalues are real and negative. And if you form the Hermitian matrix, then lambda 1 h a1 equal to -0.79 and lambda 1 h a2 equal to 3.52. So from these examples, it is clear that a1 is not reactive because it is negative, and a2 is reactive. And for these two examples, if you just give the result, okay, first I will show you the graph. So this is corresponding to a1 and this is corresponding to a2, reactive. Amplification envelope, this black curve represents the amplification envelope for a1 and for red curve for a2. The result is that the perturbations show transient growth under a2 but decay under monotonically under a1. So no reactivity occurs for this case for a1 matrix, and a2 system is reactive for a2. And if you consider another example, dx equal to a3 etc. Here all the eigenvalues are complex. Here look at this, real part negative. Here also real part negative. So these two systems are equilibrium are stable. And here lambda 1, if you form the Hermitian part of a3 and a4, it is found there lambda 1, that is the largest leading eigenvalue, 4.15, and here it is minus this. So a3 is reactive, but a3 is non-reactive. And the corresponding graphs can be found here. This is corresponding to a4. This is a4 and this is a3. It is reactive. This, look at this envelope and amplification envelope, and it is starting from the beginning. It is start decreasing, and this graph can be easily drawn using the matrix a3, a4, and earlier case a1, a2 using your software MATLAB. It will be not so difficult. You can just check the curve to show the amplification envelope. Now, those curves can be drawn using the, if you only, your intention is only to draw the curves using simulation, then MATLAB or Mathematica software can be used. Just use the norm of this. And otherwise, for mathematical analysis, how these amplification envelope are obtained, You can found just I have here will show you two examples from ecological systems. Here look at this linear system. Here this is, and the corresponding the characteristic equation is this. Its discriminant is this one, and then now this discriminant may be positive, negative, or zero. Three cases may be considered. I have considered here only two cases, greater than 0, less than 0. Two examples are selected. Look at this. When delta greater than 0, that is discriminant is positive. Eigenvalues are this one from the matrix. It is very easy to find the eigenvalue. Corresponding eigenvalue vectors can be found here in this way. And then the V1, V2 eigenvectors, and such that V inverse AV equal to this diagonalizable matrix in V inverse, and this rho T equal to norm of this. This is the formula for amplification envelope, and now it can be V E T J V inverse, and that is in this formula. And it is not directly comes from here. That is, there are some calculation. I will show you some references also. If you like, you can check. It is not so difficult. And here it is just an example, and some of you might have idea on this example. This is a Lotka-Volterra system. Depending on the parameter sign, it may be a Frey-Pieter model, it may be a competitive model, it may be mutualism between the two species. So just I have considered this to show an example. This dx1 dt and dx2 dt equal to 0 set gives q1, q2, the two equilibrium, equilibrium point, non-trivial equilibrium point that is, and this is asymptotically stable is like this. It is very simple, just the eigenvalues if real negative, and if complex real but negative. And the Jacobian matrix is this, and beta discriminant is this. The same form as in the general case I have discussed, and it is the special case for this Lotka-Volterra system. Now, if you choose the parameter set in such a way that your delta becomes greater than 0, the system is reactive. Already I have mentioned here, system is reactive, and the amplification envelope rho T becomes this one. And from here we can draw the curve. I will show first the curve, then this is the rho max, maximum amplification, and the corresponding time at which the maximum amplification occurs. Look at this. This is the curve. The next one is better to understand. Look at this. This is the amplification envelope curve. This point, amplification, maximum amplification, corresponding time is this. This is one example. And now for delta less than equal to less than 0, in similar way, I think I am way behind that time. So just the same way, again you have to find this matrix, the amplification envelope, this one. Draw the taken one example. This is a Frey-Pieter model. Just setting dx1 dt, dx2 dt equal to 0, and then taking some parameters value, it is found that delta less than 0, and we get the formula for the expressions of the amplification envelope for this problem becomes this one, and this rho max, T max, and that represent the graph. This is the amplification. So just after initially look at this, start from here. It is not immediately start decaying to the equilibrium point. There is some growth, then it ultimately reducing, and ultimately after an infinite time, it will reach to the equilibrium. That is, this amplification is very important. I am not discussing, just I am coming to the next transient dynamics and spatial pattern formation. Here, Professor Sentivilan, can I continue? 10 minutes?
Yes, sir.
Okay.
Yes.
Okay. Okay. So transient dynamics and spatial pattern formation. Now I would like to explore how the spatial heterogeneity affects transient behavior. In the absence of dispersal, the stability of the equilibrium is determined by the eigenvalues of the linearized systems. Already I have discussed. While reactivity is determined by the eigenvalue of the Hermitian part. Already I have explained. Now, here it is a connection between two apparently unrelated properties of dynamical model system. One is the pattern formation through Turing instabilities and the transient fluctuation around the asymptotically stable system. So we have earlier discussed about the transient dynamics on the non-spatial system. Here it is a spatial system. If we consider in case of, suppose we are considering population dynamics, if we consider that it is space is homogeneous, then it is different. But if we consider heterogeneous, then spaces will move from one place to another place. Spatial heterogeneity will consider, and that include in the model by taking this term. Because if we do not consider this one, then actually our model is this. But if we consider spatial heterogeneity, then it takes the form this. So at the equilibrium, if we consider for this model equilibrium, this one, perturbation, linearized system, and this is the Jacobian matrix like this. But if we consider the perturbation in this model, then it takes not so difficult. A small perturbation to u bar is the equilibrium point, and if the perturbation is we are taking in vector form, so v bar xt, then this system takes the form is after the perturbation. And when the Turing instability occurs, that in the absence of spatial diffusion term, dispersal term, it was stable. But after introducing this dispersal term, spatial heterogeneous perturbation may not decay to zero. That is, as t tends to infinity, it may not come back to its original position. And if this case is happened, then this is known as the Turing instability. And in this case, how you will determine the transient dynamics of this system? Because these are apparently two different okay, I will briefly describe it. Now, for this system, we take a Fourier transform, this one, and this after taking the Fourier transform, the matrix J, if you take J equal to A minus norm of W square D, then it takes the form after taking the Fourier transform. So you know that any partial differential equation, take the Fourier transform, maybe it will convert to an ordinary differential equation. That is the advantage, because it is easier to analyze the ordinary differential equation instead of the partial differential equations. So if you consider this one, then now look at this. If lambda 1j is the eigenvalue with largest real part. Now if for all w real this less than 0, then this one tends to 0. If this one tends to 0, then this one tends to 0. That is, the system is stable. But if any real lambda 1j greater than 0 for some w, then perturbation with this spatial frequency will grow and produce spatial patterns. It will take some time. I will just show this portion, that this ddt of this one, this is found is this. in my references, all these calculations are given. ddt of on V, this pattern, this is less than equal to this. This lambda 1 Hj is what? You know that lambda 1 Hj is the Hermitian matrix and the leading eigenvalue. If lambda 1 Hj 0, then this one tends to equal to 0, and Turing instabilities are impossible. And here we have found a very important result that here it is, look at this, Hj equal to Hj plus this one, that is the sum of two symmetric matrices Hj and this one. And this theorem, using this theorem, that largest eigenvalue of the sum is less than or equal to the sum of the largest eigenvalue of each matrix. Since both these are negative, so here this one also negative. So the conclusion, which is very important, that is reactivity is necessary for Turing instability. It is very important. If a system is reactive, then only the Turing instability occurs. And why it is very important result? Actually, the parameter set for which Turing instabilities are possible is often very interesting to us. For models with many variable and parameters, the determination of this set can be difficult. We can limit our search to that portion of the parameter space for which produces reactive equilibrium. If we can found that this equilibrium is reactive, then only Turing instability occurs. Otherwise, if we directly go to check whether Turing instability occur or not, it may be very difficult because of number of variables and parameters. So this is one very important reason, that reactivity is necessary for Turing instability. One more thing I will discuss, then I will stop. Here it is just a graph that this dash is the without dispersal, and this one and this one, and after dispersal, look at this. This is the pattern formation for two interacting species. They are given here, but I have not mentioned that two interacting species here. Just taken one example. One more interesting result, briefly I will discuss. That is, suppose we consider a reaction-diffusion system, two-dimensional reaction-diffusion system, equilibrium point, perturbation. After giving perturbation, it takes the form like this, J(T). Now, what important is that reactivity for the diffusive system, spatial reactivity. Here it is, look at this, reactivity of spatial system. That reactivity of the spatial system can be measured by this formula. It is not directly written, long calculations are there. By this formula, this inner product. Now, if we move here, that if we analyze this, substitute everything, and then we found that there is a long calculation of course there. We found that V naught equal to this one. Look at this. Here no D1, D2 are present here. That is, this shows that for a spatial model, whether model is reactive or non-reactive is solely determined by its local interaction term. So random dispersion of species no impact on this. So what does it mean? That the reactivity of the spatial system equals the reactivity of the corresponding non-spatial system. So if I ask that, if I give you a reactive, spatial system, ask you check whether it is reactive or not, you don't have to check the reactivity of the spatial model. Just consider the non-reactive, reactivity of the non-spatial model. If it is reactive, then your spatial model is also reactive. So this is also one very important result. Okay, then I will just conclude with some possible conclusions. Look at this. Here that I have been discussed here, that both short-term growth of perturbation is as important as the long-term decay. Mainly we consider the long-term behavior, but short-term is also equally important as long-term decay. Stability and resilience characterize asymptotic dynamics, and reactivity, maximum amplification and time are considered as the transient dynamics. And also, if you reactivity here, look at this, reactivity is measured as the behavior at t tends to 0, and resilience is measured when t tends to infinity. So it complements each other. And the here the one important is this one. Look at this, short-term amplification of perturbation is a real possibility for ecological systems. Here I have given only two ecological systems. One is the lockable systems, another is preparator system, and both the short-term amplification occurs in both the cases. Also, I have also several other examples that amplification occurs. So it is a real phenomenon for common ecological phenomenon. And this is also important. Reactivity of a spatial system is same as the reactivity of the corresponding non-spatial system. And this is very important. Reactivity is necessary for spatial pattern formation via during instability. So these are some important results and some possible literature that can be some works of Newgate and Castle. Several papers are there on this reactivity and transient dynamics. Some recent application can be found by Paul, very recent, 2021, European Physical Journal Class. I have also thought about the sensitivity, forget it. And one recent paper also here, transient and asymptotic dynamics of a preparator model is explained here. And this paper, how the spatial heterogeneity affects transient behavior. Here you can get some idea. Some more recent resilience can be found in this paper. Here also some recent papers where transient and resilience regarding discussions are given based on some preparator model or some other interactive population model. Thank you.
Thank you, Professor. Thank you. So this forum is open for clarification, questions, doubts.
Hello.
Students, you can raise your doubts. Yeah, even you can write your questions in the chat box if you want. Professor, I have one question.
Okay.
Since this amplification, how far it matches with the experimental results?
Experiment are actually, you know, that done for a very short time. Experiment are not considered for a long time. So this amplification helps, for example, if you find any graph of amplification envelope, look at this. Look at this.
Yes.
So experiments are based on very short time scale. Look at this. This amplification, maximum amplification occurs here. So you have to consider this one also, that how the amplification, maximum amplification at what time occurs. If you don't know, then your experiment will not validate this result.
Oh, yeah. So the time scale is this
yes.
T is the dimensionless unit, right? Time, t. What are the dimensions of t?
Dimension
Of a time, t? So this t is dimensionless or
time here it is not any
it's
empirical example. It may be day, it may be month, it may be year, depending on the problem you are considering.
Okay. Students, do you have some more doubt? Students? We are not receiving any question from the students. Okay, Professor, we are not receiving any questions from the students. Maybe they will write to you by email or something. Sometimes they may be hesitating.
Yes, if you need any literature, papers, any documents or any, you can send me mail. I will send it, no problem.
Since there are no more questions, I would like to conclude the session by thanking Professor Tapan Kumar Kar for accepting our invitation and giving a very basic and wonderful talk on transient time dynamics in population models. Thank you, sir. Thank you very much.
I am also thankful for inviting me in this lecture series on nonlinear dynamics complex systems.
Thank
you, Professor Senthil Velan. Thank you.